Okay, I guess I might as well start. Hi, I'm Jose. I'm here to talk to you about lattices. Don't mind the title Fun with Lattices. To be honest, I came up with that in maybe 15 seconds. But what I actually intended was the fundamentals of lattice-based cryptography. And we're going to see lattices, and not the order theoretic ones. So if you're familiar with, join semilattice, meet semilattice, it's not that. It's a geometric structure that has very interesting algebraic representations. So I'm just going to go into it. Why lattices? Why do we care about lattices? Lattices have been pretty central in proving some, or actually disproving some certain conjectures in number theory. Complexity theory sees lattices as kind of an interesting point, in that lattices are actually one of the few structures that there are known problems where the average case is as hard as the worst case. So that's actually quite beneficial for cryptographers, because when you go through actual cryptanalysis, cryptographers mostly care about average case hardness more than just worst case. So a lot of the time, when people take algorithms classes, it's all about the big O, but it really isn't for cryptographers, in the sense that you don't want your algorithm to be only hard in the worst case. You want it to be hard, every time that somebody tries to attack it. So a professor called Miklos Aitai, he was the one that came onto he basically founded the topic of lattice-based cryptography. So if past this talk you find it really interesting, I suggest you look up Aitai's work. And also, lattices are used in error-correcting codes. I'm not gonna get into any error-correcting code constructions, but similar to how a lot of the mathematical and cryptographic constructions are, it's about whether certain algebraic structures have hard problems for which you can find a good solution, depending on whether you have a privileged set of information or not, like a secret key. So this is going to be our table of contents. We're going to go through a quick recap of vector spaces. Then number 2 is going to be what 80% of the talk should be about, and I'll explain why. Then number 3 is technically not just GGH. GGH is one of the very basic cryptographic schemes, one of the first few using lattices. But it's more dealing with the shortest vector problem and the closest vector problem. And then a section on NTRUEncrypt, which is also a foundational encryption algorithm for asymmetric encryption algorithm for lattices. However, as a note, these are our foundational points in lattice-based cryptography. Modern lattice-based cryptography, there is no way that we can cover it in 2 hours. From a foundations perspective, we can't even cover it in 6 hours, unless the audience is purely grad students in mathematics. Pure lattice-based cryptography, the modern constructions, so things that rely on problems like short integer solutions or learning with errors, require an even deeper mathematical background. What I hope to achieve is actually inspire you to want to learn this mathematical background, because there are lattice-based cryptography is coming up on a lot of really interesting applications, like fully homomorphic encryption that basically you can manipulate while it's encrypted. And also lattice-based algorithms are hard for quantum computers. So lattices are really interesting and still very much cutting edge. They're in a cutting edge place in terms of cryptography right now. And like I said, our goal today is a solid foundation, a rock solid foundation in lattices. I do not care as much whether NTRUEncrypt sticks with you, because if you understand the lattices portion, you can just look up NTRUEncrypt and you'll get it again in another 5 minutes. If you have the geometric notion, the algebraic notions of lattices, that is what I want out of today. The encryption portions and the cryptographic portions are mostly motivational. And as such, I won't go into as in-depth proofs of the cryptographic notions, but also because cryptographic constructions need not just a proof of whether the encryption actually works, but you also need a proof of hardness, which ends up being quite long for each one that you do. So this talk is mostly about lattices. So we're going to start with a recap of vector spaces. Is everyone here, or who is not comfortable with vector spaces? Or who might have forgotten vector spaces recently? Okay, a few. Okay, we only need to go through a few definitions. So vector spaces is a collection of what everyone knows as vectors over some field f. Our field f is we're going to deal with Rn. Sorry, with the field of the real numbers, and the vector spaces are always going to be under Rn for our purposes. Vector spaces tend to be more general than that, and you can even generalize vector spaces into modules, but we're not going to need all that. And vector spaces satisfy these properties in terms of that vector spaces are an additive group where these scalar product laws hold. So the scalar product is associative, it distributes over addition, it distributes over, like, in the scalar multiplication, addition also distributes, and also the identity element of the field leaves the vector untouched. And of course, the last quantification down there just means that under scalar multiplication and the group operation, which we denote as addition, the vector is closed. So you cannot make a vector outside of the vector space just with scalar multiplication and the group operation, which is addition. So linear combinations are simply all vectors in this shape. So if you have a set v1 to vn, you take all the vectors of v1 to I said vk there, but vn doesn't matter, with some scalar, and the resulting vector is what you call a linear combination of the other vectors. So linear combinations have an interesting case, which is linear independence. And we care about linear independence of vectors in the sense that a linear independent set of vectors is one that cannot express itself, like another vector inside of the set with the other vectors. So it's basically I cannot make if I'm going to use a lot of the two-dimensional examples, but if I have one vector here which is just 1 0 and another one that is just 0 1, I put them backwards. Okay, whatever. This is literally backwards. But the whole point is that I cannot make this vector right here with a combination of scalars using this vector. And the more the basis grows, this still applies. And this is an extremely important concept. Yeah, we'll get there. Yes, orthogonality is actually quite important, as we'll see later. So anyway, when you have a linearly independent set of vectors, the span of that set of vectors is what you would call all possible linear combinations that you can make with those vectors. And when you have a linear independent set of vectors that spans a vector space, so in other words, that you can generate any vector in the vector space with that set, you have what is called the basis for the vector space. And the number of vectors in that basis is your dimension. So, yes. Well, it is, you can have more than one basis, but they are essentially isomorphic.
Every vector has to be generally uniquely from the basis.
Yes. Oh yeah. That's also a condition too. That's correct. So every vector has a unique linear combination, and yeah, that's actually an important fact that I don't have there. But yeah, do take into account. We actually use that fact in one proof later on. So thank you. And then here's just a few general points or a few statements about vector spaces that you should keep in mind. So for any vector space, there always exists a basis. Any two bases of a vector space have the same number of elements. And the dimension of the basis cannot be larger than basically the dimension of the underlying space. So you cannot have, a basis of you know, R2 in the case, right? That is larger than just 2 vectors. Because if you notice, you can always generate every single vector in this space with just those 2. If you take any 2 real coefficients, you can go anywhere in the space that you want. There's a very simple proof for that, but I'm not going to get into that. But it's if you guys want, I can prove that later. Anyway, the dot product, generalized, that's called the inner product. But the dot product is the one that we're going to use the most. It's simply a way to take 2 vectors and return a scalar. That's actually the general point of a inner product. The entire point of an inner product, in the sense, is in the general sense, it generates inner product spaces, which also are linear. So the inner product as a function, as an abstract function in algebra, is linear. So it preserves operations. But in the simple dot product case, you simply take the vector written out in component form, and then you simply, you do the addition of every single component multiplied with each other, right? So it's just that simple sigma. And then the Euclidean norm, or what most people think of as distance, is that, which has a relationship to the dot product of v dot v is the same thing as the Euclidean norm squared. And that's actually pretty simple to notice that in the easy case of R2, that actually corresponds to the Pythagorean theorem. I use R2 a lot because it's okay. For one, I can't even draw in R3. It would be really ugly. And then the second part is that it's a lot easier to envision things in R2, but when we're going to talk about lattices today, we're going to work in Rn, and I can't even picture a lattice of rank 15. So it matters that we get the general gist of it with R2, but then that we can expand this notion onto higher dimensions, because that's actually how we can encode more data. We can play with vectors of longer size. That's why that's important. Again, this is just definitions, so feel free to just, while you're going through this, refer back to these if you forget anything. Anyway, Cauchy-Schwarz is just saying that the dot product of 2 vectors has an upper bound of the multiplication of the norm of the 2 vectors. And then the next definition is 2 vectors are orthogonal if their dot product is 0. In the case of R2, that just means they're at a right angle. So it would be like this. There's a vector here. There's a vector here. That also works in 3 dimensions, and then n dimensions. There's also one. We're not going to use it, but I'm including it for fun. It's that you have, I believe, v dot v. Oh no, v is the same thing as vw cos theta. So the dot product of 2 vectors is actually equal to their Euclidean norm times the cosine of the angle that they form together. So if you have a vector going this way and another vector going this way, this is the theta between them, then the dot product is that quantity. Just for fun, we're actually not going to use that one at all. Yeah, this one's kind of dying. Sorry about that. Okay, right. We got to lattices pretty quickly. Right, so what are actually lattices? Lattices are kind of like a set of points, an infinite set of points that display some sort of structure. It's super easy to visualize in R2. One note is that they don't actually have to be, that's actually a good graphic in the sense that they're clearly not just at right angles, right? A lattice in R2 is not this grid, right? Like if this is the origin, this is technically a lattice. This is a valid lattice, right? But if you have another space here, if you were to draw something like this, all the intersection points here, these are points on the lattice, right? So it's a grid up to R2, and then you have to kind of try to envision it in higher dimensions. Yes, that is a very good point. Yes, it does, and we'll get to why. I don't want to spoil it. It's fun. Anyway, so the actual mathematical definition is that it is a linearly independent set of vectors. It's basically kind of like the span of a linearly independent basis, or sorry, all bases are linearly independent. But it's basically the span, but all the scalars are integers. That is the easiest definition I can give you. So it's just that little set right there. So it's just AI, BI. So BI is one of the vectors in the basis, such that AI is in the integers. But it's not just a set of linearly independent vectors with that. It also has a really interesting condition, which is that it's a discrete kind of vector space. What does that mean? And the easiest way to show you is around every single point of the lattice, we can actually draw a ball. So let's say in this one, let's say the radius is something like this, about which you only contain one point in the lattice inside of the ball. An equivalent definition of that is that there exists a minimum distance between two vectors, two points in the lattice. Remember that when we talk about the lattice, we're talking about the discrete points themselves. And the interesting bit about the periodic structure is that you can see that in the R2 case, which is the easiest to see, you can kind of see that it kind of goes up in units, right? Every time you add, you increase a scalar in the lattice, you kind of go up by like a little block. But yeah, of course, this extends to Rn. So in general, for n dimensions, we talk about the Ndimensional ball. And it's basically saying that there exists a minimum radius such that you can always make a ball around one point in the lattice, and there's not going to be any point. So in a sense, it's a least upper bound. Yes?
I'm a little confused about, we had our basis vectors are orthogonal, maybe?
No, we haven't talked about orthogonality at all.
Because it felt like that to me, but then when you've got this thing that's skewed.
Well, they don't have to be orthogonal. They can be. For example, I'm going to come back to this example a lot, but the easiest one, yes, they're all linearly independent. Otherwise, it's not a basis. Basis has to be linearly independent. The set itself, I mean. But linearly dependent just means that I can take any two, or not any two, but there exists some vector inside of that set that I can that I can state in terms of the other vectors. So I can make a linear combination of the other ones and make one of those, right? So why I brought up the linearly independent case in R2 is just because you can see in the super basic case that with this vector going up straight in the y, okay, this is taking me off. I don't know why I wrote it backwards. You can't ever go up in the x direction in terms of the y direction. That's the easiest case of envisioning, or sorry, like putting linear independence in your head. And when you get to more dimensions and more larger bases, the idea stays the same. That you just simply cannot express one in terms of the other. And an equivalent definition is that if a linear combination of your basis is 0, that means every single scalar in that combination is also 0. So the only way to get the 0 vector is for every single one to be the 0 vector. Orthogonality is important, but we won't see it for a while, but it's important. But just do note that a basis does not have to be orthogonal. There are really interesting properties when it is orthogonal, but it does not have to be. And we will talk about very soon what relates multiple lattices. But okay. So, oh yeah, and we will touch on a proof right here. So it actually, any subset of Rm is lattice only if and only if it is a discrete additive subgroup. This is an interesting property. So it's basically saying if you have an additive subgroup and you can always draw that ball, then it turns out to be a lattice. But we will prove that. That proof is actually really trivial after we introduce a whole set of machinery for it. But we'll get there. So we define a fundamental parallelepiped as, and the fundamental parallelepiped is not a lattice. It is, you can think about it as a property of the lattice. I'm going to explain it in layman's terms first. When you have your little grid, if you were to fill one of these up, that's your fundamental parallelepiped, right? Usually it's about the origin, of course. But you can kind of see that it kind of tiles our lattice space, right? So, mathematically, it's just the actual set of basis vectors, and instead of, what's it called? Integer coefficients, every single coefficient is between 0 and 1. And that's pretty easy to see. In R2, that just basically means that you can take like the tiny steps and fill in every single little quadrant there. So if I let's say my basis vectors for this are here, and man, I should have drawn this about the origin for it to be not ugly. Let's see, it's one of these. Then I can take little steps like for example, some coefficient here plus this one gives me a point here. Anyway, the entire point is that it's the set of linear combinations that give you all the vectors inside of that little region.
xi being R?
Sorry?
Those xi's seem like they're some R.
Wait. Okay, no. Xi, it should be an R. Yes, you're right. I don't know why that's Rn. It should not be an Rn. You're right. Yeah, because that looks like it's vector multiplication. It's not. Right. Sorry. That should be an R, not Rn. But they're supposed to be coefficients. I could have just skipped the group. Sorry, the field it belongs to entirely. All that matters is just basically that they're between 0 and 1 exclusive. So you don't actually hit an integral value. So actually, before I get to this slide, what do you guys notice about the fundamental parallelepiped? It kind of tiles the whole place, right? Like just kind of looking at it, right? What if you kind of just move that around, up? You can kind of fill the whole graph, right? And this actually has a mathematical notion. But this slide is just what I'm saying right now. Just by naive inspection, we can kind of see that it tiles the place. And then the other little interesting bit is that we notice that the fundamental parallelepiped gives us some sort of notion of area or volume. Now, before if anybody that's good at analysis, I don't want you to destroy me and telling me that the reals are infinitely dense, so you can't have volume in terms of sets. So that's definitely not what I'm getting at. I just want to get informally introduce a notion that we have kind of like a region that we actually can measure. That's kind of what I want to get at. So it turns out that these intuitions are actually correct. And it gives us a notion of actually, it gives us actually a partition of the vector space in itself. Are you guys familiar with partitions? Okay, good. I don't have to explain that. And it also gives us something that's called a volume. Now, however, the volume is actually something that people learn in linear algebra, but it's one of those linear algebras full of like fun facts that people forget all the time. But the determinant of any parallelepiped, like what's it called, in Rn is it's volume, it's sign volume, and there's a sign because there's some rotation going on there if you multiply the volume quantity. So we don't really care about the sign, but all right. So this is what we're gonna try to prove. If L is a full rank lattice. Oh, and by the way, we're gonna deal with. I didn't explain what full rank lattices are. You guys can notice that the basis of a vector space is bounded at the top by the dimension of the actual space, but you don't actually have to have the basis be the same length as the space. However, actually, when you have the basis being the same length as the space, you actually have you can always form square matrices in terms of the basis vectors. So R2 case again, if you have 1, 0, and these are just the elementary vectors, and 0, 1, you can of course you can put these in terms of the identity matrix, right? And it's a square matrix. So we mostly deal with full rank lattices. So basically lattices that the basis itself is the same dimension as Rn. But I do need to note that that this refers to specifically for a full rank lattice. And there is actually a generalization of this if you are interested, but it's a much longer proof. So if we have a full rank lattice L, and F being a fundamental parallelepiped for it, let's try to prove that it actually spans all of Rn. And that we can actually tile all of Rn. We need to prove it somehow. So what we're trying to prove is that we can write every single vector in Rn as basically a sum of one of the points of our lattice and our fundamental parallelepiped. And graphically, you can think about that as moving. So if this is your parallelepiped at the origin, right? If you move it, with a vector here, you get the parallelepiped down here. And you get all these origin points in here. If you move it by the sum of these two, you get a parallelepiped down here. That's the notion that this is trying to capture. This is a fairly simple proof. And again, at the bottom, it just says that equivalently, this does form a partition of Rn. So for every single point in the lattice, this will give you a partition. And the partition is just simply the little shaded area. That's what it is. So that in itself, there's an infinite number of them. But they do, when you take the union of all the tilings, it spans Rn. So this is how we kind of think about it graphically. That's what I just went through. It's kind of the notion of translating the parallelepiped. So this is our proof of our little conjecture. It's fairly simple. There's the more thought out and long way. But the easiest way to think about it is and every point in Rn is in Rn, not our lattice specifically. Oh no, I dropped every point in Rn. We know it as something like this. AI, BI. Our basis, of course. We're going to have some basis for Rn, BI, B2 to Bn. Okay? Remember that a basis spans the whole vector space as a linear combination. So we have, plus An, Bn, right? So the default case is that this is in R. So you have every AI is in the reals. So what we want to do is write it in terms of our lattice and our parallelepiped. And this is actually way easier than it should be. That's why it's so nice. The real ease to it is that you can notice that lattices are always integers, like the scalar values that they go up by is always integers. And the fundamental parallelepiped defines the region between the origin and right before the end of the vector. So you can always take, I'm not going to write it, but the entire point is that you can take some alpha from the lattice as a scalar from the lattice and some ti from your fundamental parallelepiped, and due to just the property of distributivity over addition, you get this alpha bi plus ti bi. And now we partitioned it in terms of our fundamental parallelepiped. And this is without loss of generality. It doesn't matter which one you pick. Just because when you write your sum vector w, you're going to get that little sum, which is the same thing as saying alpha I v bi plus blah, and then plus t1 plus blah, t1 b1. So the only thing that we need to, sorry?
I have a question.
Yes?
Why do we need to use vector space to do this?
It's like for simplicity.
So far, we've
You can generalize it more.
okay, into like modules.
Yes, you could generalize it into modules, but well, mostly because a lot of the times you do, like when we start seeing upper bounds and lower bounds on specific properties of the lattice, then you need to be in a vector space because we're talking about directly. For one, we're talking about a vector space in Rn, and we're talking about the specific direct product of the dot product. So that's mostly why we need to be in a vector space. We need it to be a field. All right. So anyway, the only half of this proof left is Emily's her point in that every single linear combination spans a unique vector. So we just need to prove uniqueness, and that one's easy. So without loss of generality, just take any the thing that we derived in the last step. We take any ai plus ti bi, and then let's imagine that there's a different one that comes from a different vector that somehow gives you the same component of that sum. Then it turns out that if you assume that they're equivalent, you can always rewrite. You can just do algebraic cancellation and rewrite the exponents in terms of ai minus ai prime and ti minus ti prime. But that one's fairly simple because every single all the alphas are not ai alpha, but all the alphas are integers. So of course their difference is going to be an integer. But because ti and ti prime are reals, the only way that is going to give you any integer is if they're equal. So if they are exactly the same. So that's a fairly simple proof of uniqueness. It just shows that whenever you pick a specific scalar or just a specific vector, you're always going to get a very unique point in the region using the lattice plus the parallelepiped. So this is why specifically we care about full rank lattices. Another way of thinking about them is, well, I mean, it's still kind of the same way, but instead of just thinking about the lattice in terms of the vector space spanning in terms of some linear combination, you can rephrase it in terms of a linear transformation. If you put all your B1 to Bn, your basis, in terms of a matrix, you can always rewrite it in this form, where LB is all integer vectors in Zn, and you just have the matrix multiplication of Bn and X, and it turns out to be exactly the same. If you do I'm imagining that I don't have to explain matrix multiplication, but if you're curious, try it by hand, and you'll see that this is exactly the same formulation of how you add, and the simplest way that you can observe it is just because of the way that matrix multiplication works, that it goes row by column. It's always going to match the first coefficient to the first Bn and so on and so forth. Right. So what we're interested in now with this sort of new property is how do we actually if we have this let's say this two-dimensional space, and we might have another vector that just goes here, and then another one that just goes here. I'm bringing up random ones. When do these two actually give me the same lattice? Let's say that these two are a basis. Let's not think that they're exactly the opposite, because then they would be the negation. Let me add a better angle here. But when would these two give you the same lattice? So this becomes a kind of like an interesting point in how do we categorize lattices. So if you want an example, the first two are linearly independent column vectors. They also generate the exact same lattice. But the third one is a linearly independent set of column vectors as well, but it does not generate the same lattice as B1 and B2. We want to know why. We want to understand why, and it's not that complicated, but it requires just a little bit of machinery. So we say a matrix U is unimodular when basically the determinant is plus or minus 1, or sorry, positive, negative 1. And it turns out that we can relate any two bases, B1 and B2, via unimodular matrices. And actually, we can relate them if and only if there exists a unimodular matrix where you can turn B1 into B2 using a linear transformation with it, or just matrix multiplication, however you want to think about it. So we're going to prove one way, and then I'm going to go for, ask you guys about the the converse way. So we're proving an if and only if statement, so we have to prove the first way. So we're going to assume that we have, two bases that describe the same lattice. How do we know that there exists some unimodular matrix that describes them? So, let's say that this implies that there exists some matrix, right? You can apply, you can apply the argument in the first way. So you can let's say that what's it called? We know that every single column vector of B1 is linearly independent, and B2 also spans the same space. So we have that every single column vector of B1 is in the second lattice. Sorry, I got jumbled up in my own proof. But what this implies is that because we can get every single vector in terms of the second lattice, right? And remember that we restated lattices in terms of linear transformations. That means that there exists some linear transformation, right? That takes our B1, that gets us B1 from B2. And just switch B1 and B2 and you can actually do the same argument backwards. But we don't know yet whether they're unimodular. We just know that there exists some transformation. Just simply because they're two bases that span the space. So we can actually do very simple algebraic substitution. And remember, these cannot be non-singular matrices. These cannot be singular matrices. Singular matrices being a determinant of 0. So they are invertible matrices. And this is just a property of having a matrix in terms of your column vectors is if they are linearly independent, it is non-singular. This is just a linear algebra factoid. You can prove it, but anyway, if you perform the same algebraic substitution, so we simply apply the same logic, one way and then reversed it. So, we put B1 in terms of B2U and then B2 in terms of B1B, and via simple algebraic, substitution there, we cancel out the B1s, and then we get that VU is the identity, right? And well, we're pretty much done because we know that these unimodular matrices, and specifically in our lattice case, they are integer matrices. So there is no way that we can have a multiplication like, the determinant of, so if you guys forgot, just a very simple fact of determinants, you have the determinant of AB, the same thing as the determinant of A, det A times det B. Oh my God, I need to erase. But because of this, there's no two integers that are going to give you 1. Remember, the determinant of the identity is 1. So that means they're either both 1 or they're both -1, meaning that we've proven that they're unimodular. And now let's do the converse together. So we're going to assume we have unimodular matrices, right? And two bases. How do we prove that they are, that if we have a unimodular matrix, two unimodular matrices that relate to two bases, how do we know that they refer to the same lattice? Does anybody have an idea of where we could start? So if we have two unimodular, if I'm going too fast, then please let me know. Or if I'm talking too fast, not so much going too fast. I'm trying to be understandable. So if you have, remember that we have, so two bases generate the same lattice, if and only if we have unimodular matrices that transform between them, in a sense, right? So we proved that if we have two lattices that are the same, then there exist unimodular matrices, correct? Now we need to prove that if you have a unimodular matrix that relates to bases, that they generate the same lattice. I'll give you guys about a minute to think about that. No, because I actually left that specifically out of the slides, so we could do it.
How do you do it in general?
Well, I mean, you need to start with some assumption, right? We're just writing a proof. So
And we have, so like human modular and we have two bases.
yes,
Say whether or not those lattices.
right. Hold on.
that we can find.
Let me erase so I can put your thoughts into proof form. Yes, you're very close. But yes, it is quite literally this. So when we have B1 and B2, these span Rn, right? And then we know that there exists some U such that U is unimodular. Modular, and we have let's go with the B1 case. B1 is B2U, right? So the proof of that is actually kind of contained in the other proof. It's
Another unimodular matrix.
yes, but yeah, but okay. Do you remember what is the determinant of the inverse of a matrix? It's just 1/d. Yes. So the entire point is that because the what's it called? This unimodular matrix is non-singular. It is invertible. So we can go this way. We can go. Oh, sorry, I'm using the wrong marker. I keep forgetting. Where's the? Oh, okay. Okay. So we can go this way. B1, 2, B2. We can take a column vector here just because we know we have U, so we have a linear transformation, right? So we know that essentially every single basis vector. So remember that B1 is this. It's just let's call it B11, B12 to B1n, right? All right. So we know that we can always get every single element of these in terms of B2, right? So that actually means that our lattice of B1 is actually contained in the lattice of B2. And how do we prove the converse? It's quite easy. Well, we know that this has an inverse, right? So we just perform F cancellation on this equality right here, and we can prove that that lattice of B2 is a. My writing is really ugly. Lattice of B2 is a subset of lattice of B1, so they are exactly the same lattice. That completes that proof. It's not. So anyway, we've proven now how to relate two different lattices. There's actually there's a deeper connection which is kind of cool. In that I don't know if you guys were thinking about it, but you know how you can have a lattice with different bases, but you know that the lattice is basically the same points. So because the unimodular matrices are, the determinant of them is 1, and the volume of a lattice is just the determinant of the base matrix, right? The only way that you could generate the same lattice, the same volume of the same lattice, is if this, is if this property would hold. Would be det B2U, and which is the same thing as saying det B2 du, which, because it's 1, it holds. So it turns out that no matter your basis, you're always going to have the same volume of the parallelepiped. It's obvious if you look at it graphically, but it requires some nuance to prove mathematically, and that's half the fun. That's why we're here. So
Geometrically, this kind of looks like you're either going the same way or
yes,
the exact opposite way.
exactly.
That's the direction of the original lattice.
Yeah, the original lattice, because you usually just root it at the origin, and it makes your life easier.
Yes.
How we doing? Okay. So, cryptography. We can think about cryptography as the study of one-way functions, Who is fairly fresh to cryptography? Is anyone okay? Well, you're not fresh. You don't lie. So, in a lot of cryptographic constructions, you guys are probably not familiar with the math behind cryptography, but you're familiar with what it does, likely. When you turn on HTTPS, you want bi-directional communication, but you don't want an eavesdropper to peek into it, right? You need some way to hide the data, like that data, in such a way that with your key, with your little key that unlocks the little box of your data, that it's easy for you to compute with your privileged amount of information, in this case your key. And for an attacker that doesn't have your key, that is hard. So they want none of that. They want to be able to, they want you to pick a bad algorithm and for it to have good properties so they can just crack it. So why, in terms of one-way functions, in general, for one-way functions, as a little disclaimer, are only a theoretical bit. They are not proven because the existence of one-way functions would imply that P is not MP. And we all know that that's not solved. That is basically because a one-way function is, in the notion of it, is it's easy to compute, hard to reverse. That means, that means like finding the solution is, not like might be in non-polynomial time, but computing it might be in polynomial time, right? So that is the very basics of the problem. So to an extent, cryptography is practically an unproven field, but I mean, we like cryptography does rely on the P is not MP assumption to some extent, and this is why we don't actually have certain hard proofs for cryptographic constructions. Cryptography is actually, it's heavy on proofs, but it's very heavy on statistical proofs. And there's even such a subset of cryptography called, very like provable security, that is based on, like harder statistical proofs. Just because of when we state certain problems that give us this one-way function property, right? What happens is that we actually don't we just don't have an algorithm that solves it efficiently. And for some of the well-known problems, we have like lower bounds of how hard is it in the worst case, and we have things like this. But for example, if some guy found a way to solve the discrete logarithm problem, which is discrete logarithm problem is basically this: if you have a group. Well, you know what? In a general sense, we don't use modulus because a group doesn't necessarily have to be a number. But it's finding, this like how many n's within P, right? That is the discrete logarithm problem in a nutshell. When you take it, for example, with a construction like RSA, then it becomes number theoretical. So we're dealing with some mod PQ, right? And for example, in the case of RSA, again, this is very hand wavy because you don't really have to. We're not going to go into it very much. But for example, in RSA, cracking this depends on. Well, actually, RSA is a little bit different. It's actually this. It's this. No, it's this. X is equal to. But. Yeah. Yes. No, actually, no. Well, you technically. Well, you need the. Good question. I don't exactly remember if RSA requires a field. I know it requires, because I don't know if RSA is like the points on RSA are only the units, or it's every single point from 1 to PQ. I just know that when you take the, you need to take an invertible point. That's it. But I don't know if. Yeah. Of course. You have to choose only the invertible elements. Sorry. Yeah. Okay. Anyway. So if this is a prime here, we have the very basic DiffieHellman problem of finding how many, and this is now, this is a prime, this is some number modulo p, and this is some x, and it's finding this n is hard. Like I said, I'm not going to go into it too hard, but the whole gist of it is we haven't we as a society haven't solved the DiffieHellman problem. We have an idea of how hard it is, but there is no concrete proof that it's never going to be, beaten ever. However, there are proofs that quantum computers have a much easier time with the Diffie-Hellman problem. This is the whole point of post-quantum crypto. But I'm not going in there. But that's the general gist of cryptography. We're looking for one-way functions. We're looking for ways that we can use some algebraic structure. So, it could be the field of prime numbers. It could be elliptic curves. And we're looking for a property that if we have some privileged information, it's easy to compute, hard to invert. So for lattice cryptography, we actually have very similar problems. Problems that fit that sort of description. And these are very well studied. Now, again, I am going to restate, this is the foundations of lattice-based cryptography. The most cutting edge, most modern constructions are based upon something that's called learning with errors, ring learning with errors, and short integer solutions, which I will not go into because, for example, short integer solutions requires more background on discrete Gaussian distributions, which I am not covering today. But the essence of it is still somewhat similar. They are similar problems to SVP and CVP in that they're more probabilistic in its, whether you can find a particular, like in short integer solutions, you're trying to find a specific vector with some property, which is, it's smaller than some sort of amount. I'll go into it later. That's a bonus. I want to really cover the fundamentals more. But just as a note, as a side quip, these are important to learn the fundamentals, but they are not what you would base on, like what the super modern constructions are based upon. They're much more complicated, but this is a very good start to understand them. So anyway, it turns out that for certain lattices, finding the shortest vector is actually not that easy. So that is the shortest vector problem. It's just basically minimizing the Euclidean norm, like the length of the vector, and finding the smallest one. And kind of a very similar problem is the closest vector problem. And it's if you give me a point, can I find you the point on the lattice that is closest to your point in Rn? So just find me the point that is the closest. We will actually see CVP more specific, like more in depth. Something not on the slides is that actually CVP is somewhat harder than the SVP. And because CVP can be reduced to the SVP with higher dimensional matrices in certain cases. So in the general case, CVP is harder. And you have the approximate, shortest vector problem, which is the same as CVP. Find the min, except find it to some function, to some factor. It could be that phi n is 2n or phi n is 2. Depending on what lattice you are and what specifically you're looking for, the properties of that function, you will choose that function. And the approximate CVP is the same. Like if you're minimizing, so the approximate CVP will be like if we have some w in Rn, find some x. Well, let's say that we have some x in our lattice L. And L is our lattice. Find the minimum of this, or x minus w, w minus x, it doesn't matter, such that you basically minimize the CVP, which is basically the minimum. You have some phi n, and then the minimum of what's it called? Some vector minus w. So imagine this is your shortest vector, like the vector closest to w. You want to find some x that is within that bound. The smallest x that is within that bound, within this phi n times your actual minimum. We'll touch on that a bit, actually. But so that's actually 2. Do you guys want to take a break? It's been quite a lot. You guys want to take a 5-minute break?
Yeah, sounds good.
Okay, let's resume in 5 minutes. Am I speaking like a machine gun again?
Okay.
I do that a lot. I don't know why. Just a problem.
It might be a little fast for people that are new to the subject.
No, I know. And by the way, now that we're taking an intermission, we only have 1 more hour. If you're lost, completely lost, or anything, just tell me. This is the really great part about small sessions like this is that we actually have time to go like case by case, and I can help you understand something that you might not know. If you're struggling, if you're not, then you're all great mathematicians, and it's awesome. That's the ideal.
Yeah, I don't know about being great, but if it involves BS, I can excel. I'll claim that.
That's good timing for that.
I'm still struggling with the orthogonal.
Well, you don't have to think about just
So I
ignore orthogonality.
Well, I'm
Until I bring it up again, just don't think about orthogonality at all.
well, I guess I'm trying to understand the definitions because
It's just they're at right angles.
There's only one definition of orthogonality. The dot product is 0.
Yeah.
but I thought that was linear independent. It was
No. The linear independence is the linear combination is only 0 if every single coefficient is 0. Remember, we have linear combinations and dot products, and they're completely different. Linear combination is you just take a scalar and the vector, and then you sum up the whole basis, and then you get another vector. That's it. Okay. Orthogonality means the dot product. Remember, the dot product is a completely different quantity than a linear combination because the dot product is a scalar. So with a dot product, or in general an inner product. Yeah, go ahead and play with it. You have 5 minutes. A dot product will always give you a scalar quantity. Whereas a linear combination of a vector gives you another vector.
So if you imagine every vector, right, is a finite formal sum of some A and some B n, where an is in your
Field.
your ground field, and your bn is in your vector space. That's a vector, right? So any two vectors.
Because remember, vectors are closed under this.
Are linearly independent if when you add them together.
Yes. Well, all linear combinations.
You take all linear combinations and sorry, there's actually one.
So when you take all linear combinations, you cannot have any of them give you the 0 vector unless every single coefficient is a 0 vector. So it's basically saying I cannot make the 0 vector unless I have the 0 vector to begin with.
Or if these guys are literally.
Yeah, exactly.
You must be able
Or-
to find an inverse.
I mean, the easiest way I like to think about it is just, I can't make one vector in terms of the other one because that is an equivalent definition.
So you must have something that is exactly inverse in order to find a linearly.
Yeah, I think I've just been using the
Yeah, don't.
This is funky. It takes a lot of hacking around to actually get. What you're seeing also in here is is kind of embedded in this is an explanation of why no one will let go of talking to you about dimensionality. That's inherent in these equations.
We will see orthogonality.
probably 30 years ago.
The inverse definition is interesting because then it gives a good characterization to the dot product. So orthogonality is defined by a dot product that is 0, right? So which means that for all pairs of A, I, and B, I, in your ground field, then they are multiplicative inverses, and their sum is 0. Or sorry, they annihilate. Sorry, they go to 0.
There's also an easier way. Do you remember what the cosine of a right angle is?
Yeah.
0, right? Okay. So you take any two vectors.
Right.
Okay, I see it
So
now.
that's what we refer to as an annihilator.
Yeah. But I'm just giving the example.
They exactly cancel each other out from like an angular point of view. But in effect, that just means that they exit out of the group of units through multiplication. So it's not closed in the field.
Right.
It's
So.
very closed.
So yeah, if you guys remember, this is simply just the norm times some. If this is your theta, VW, and cosine.
Perspective of dealing with latitude and longitude.
Mm-hmm.
And then, you got your vector bundle.
Well, in your case, if you have a latitude and longitude, you're dealing with R2. Just any two, coordinates that are at right angles, they're orthogonal.
Even dealing with climate change, like usually you use the stereographic projection in R2, which is
Yeah. Well, it has to be validly calculated.
yeah.
Okay. Is everyone back? I think there's one person missing.
Right. Right. You're not dealing with weird vector spaces where you don't have orthogonal.
Yeah. All right. It's been around 5 minutes. He'll be back. Or if he's not, then he lost his book. Okay. So where were we? Okay. Yeah. So as we saw in the SVP, the entire problem is based around the shortest vector. That's the whole thing. And we come back to the discreteness definition. You guys remember that, a vector, it is a lattice if every single point is discrete, but we don't have any way to prove that discreteness yet. But we have a way of formulating what the shortest distance would be. Also, I think there's one definition that's missing there, which is the ball around some origin. But you know what? In this case, in the easiest case, most of the time, it's easiest to think about vector spaces about the origin. That's usually how you think of basis, right? So we can always make an equivalent definition in terms of this thing. So I just want to point out that B 0R, and why this is 0 is because you can actually have a ball rooted around a new point, right? So B 0R is talking about the ball of radius R. The two-dimensional thing. This is actually n-dimensional. This is the n-dimensional definition. But again, I'm not talking about only the two-dimensional ball, because in the two-dimensional case, it's just a circle. But we're talking about the n-dimensional ball of radius R around some point. And this ball could be around this point here, right? We just don't care about that. But the definition itself is actually quite simple. Basically, you have. So this is the open ball. I'll get to the closed ball soon. So it's basically saying the set of vectors where their length or their Euclidean norm is smaller than this, and this is what you call the open ball, because it doesn't if your vector length is exactly R, then it's not in the set. So the closed ball is just B, is B and then the little dash, and just take this exact definition and add less than or equals to. I'll actually write it just in case.
So this is just saying when I translate by integer coefficients in my vector space,
remember that this R is in the reals. This is not necessarily integer ball. It's not necessarily integer ball. However, I mean, you have the right notion in the sense that when we have the smallest length of vector, it will be an integer. But the definition of the ball does not require R to be an integer.
Oh, this is just general.
Yes.
Is it 0 in the index, B0R?
So this is 0. There's just the ball rooted around 0. Otherwise, then you have to actually take the difference.
I just wanted to make sure I got it right.
We mostly care about the one around 0 because we're going to use it. So simply stated, you guys know you guys should know what a greatest lower bound is, right? It's basically the smallest of if you have some subset, it's the smallest element of the subset that is smaller than every single other one inside of your subset. So it's a member of the containing set. But in this case, our greatest lower bound will actually be in the subset because it is the closed ball. So what this lambda 1 is saying is that basically the smallest distance, the shortest vector, is within the ball. So it's basically however many, like the smallest vector and the smallest ball that you can make would be if you take the intersection of points between your ball and your lattice, right? Your closed ball, remember. So you can hit another lattice point, but such that there is what's it called? It's lower bound by 1 in this case. And by the way, for lambda I, you'll see that this becomes I. So this is actually called successive minima, but that is the actual generalization. But it's just basically saying that the smallest one is gonna the smallest vector is gonna be contained within some ball around the origin. That is kind of the general notion of a lattice. It's really easy to see graphically if you just start at the origin, draw your little lattice points, and then you'll find that there's gonna be some radius of ball that you're gonna hit 1 point first. You might hit 2. I mean, if it's a square, the super square one, in which case you technically, I mean, it's the same one, but sorry, like ultimately the entire point is your ball is going to contain, you're taking the greatest lower bound of that specific, of the smallest space that contains this. So what we're really trying to say mathematically is that we're looking for the radius such that it is the smallest that contains only one point. So we have a space with only one vector. That's what we're trying to do. So it is equivalent to saying the smallest distance. Yes?
How can the lattices avoid having a lattice point at the origin such that an arbitrarily small ball would just contain that point at the origin?
Oh, well no, sorry. Well, we're looking for a non-zero vector. You have a really good point. I forgot to mention. I guess I thought it was implied because like the trivial solution isn't really, I mean, it is trivial, so you would solve every cryptographic problem. But sorry, we are looking for the smallest non-zero vector. So this does not contain the trivial solution.
Okay. So the trivial solution was trivial.
Yes.
Okay.
So you're not wrong. You're technically correct, which is the best kind of correct. And anyway, the little interesting little tidbit about this generalization is that you can actually, if you were to view it on like kind of like an angular lattice, you'll see that maybe you'll hit like the first ball is here, right? And like let's say this is your shortest vector, or sorry, like here, sorry, same thing. But it might be that next time you try to capture at least 2, you end up capturing more. That's why there is this greatest lower bound condition. We're looking for the smallest ball, but it might be that the second successive minima only contains, it contains more than 2 vectors, or so this definition makes us think. But it turns out that that's actually not the case. It turns out there's a correspondence between the indexes of successive minima and progressively bigger vectors. Sorry? Okay. Again, this just goes back to the discreteness property, which we haven't proven. We will prove through proving successive minima, which is interesting. But all right, the successive minima is probably the most involved proofs in this whole talk, just because it is so central to the shortest and closest vector problems. We just simply just to give you a preface, successive minima and basically the shortest vector matter because we want to have some sort of measure of how can we bind, like what's our shortest vector gonna, like what is the minimum length it's going to have relative to, let's say, like the dimension or the rank of the lattice. Like, can we get an upper bound and can we get a lower bound? We care about that because we care about, for an n-dimensional lattice, how hard is the problem going to be approximately, right? These are measures that we care about when we're tackling hard to invert problems. So that's why we're going so in depth in regards to the proofs. So now we're going to proposition something. If we let B be some basis of some lattice LB of rank n, then I didn't cover Gram-Schmidt orthogonalization. Are you guys familiar with it? No, you don't have to know the formula. You just have to know that like Gram-Schmidt orthogonalization will produce. Okay, I'll cover it. It's a cool proof. But But the basics of it is that it will produce an orthogonal. Yes. No. Orthogonal matrix. So if you have an n by n matrix, when you pass it through the Gram-Schmidt machine, you will get another matrix, but the column-wise vectors are going to be orthogonal to each other, right? Back to orthogonality. I hope I don't confuse you with that, but basically, we're going to conjecture that our shortest vector length, right, or the smallest ball, however you want to think about it, is lower bound by the smallest orthogonalized vector. That's what we're trying to do. We're trying to prove a lower bound here. So if we orthogonalize the basis B, one thing I will note, so you guys don't confuse yourselves, when you orthogonalize B, you do not necessarily get the same lattice. Actually, you don't even get a lattice at all because orthogonalization uses it uses real numbers for the actual calculation. Or even like, let's say, you get the best rationalization ever and you get everything in the rationals, you still get vectors that are not lattice. So you know that the orthogonalized B is not your lattice, but it does give us some properties. We know that when you take the orthogonalization of B, then every single column-wise vector is going to be orthogonal to each other. So this is our proposition, and this is what we're going to try to prove. That the orthogonalization of our B is going to be basically the smallest one, the smallest basis vector of our orthogonalized matrix is going to be the lower bound on our ball. So, all right, one thing the way that Gram-Schmidt works is that let's say we have really hope I don't muck up the definition because it's a long one. But if we have some basis, right, v1 to vn, this is our basis. Let's call it BA. I don't know. I'm stuck with variable names even in code. So this is our basis, right? Gram-Schmidt orthogonalization. It goes from basically, you start with your v1 is going to be your vi. And then you basically, your vi star, and this is your orthogonalized vector, is, if I recall correctly, I might have to look at my paper on this, but it's this sum, mu of I think it's ij. I'll define what mu is, times less than j, I think, vj. Okay, I'll explain what this is very soon. I have to double check my notes. I just don't want to muck up this definition because it is quite important. All right. Might not have it. Do I have it in the next slide? I believe I do. Let me see. Oh yes, I do. Yeah. Anyway, the whole point is that essentially you take the sum of so this mu quantity right here, bj star. Well, what it's basically doing is that you loop from the beginning, and then you start with this one. You don't touch it. Then, because we're done with this one, we don't have any precursors to deal with. Then you take this vi, and you subtract this mu quantity, which is mu of ij. If I recall correctly, this one I do have the definition for. Yes, it's vi. So the actual vector, not the orthogonalized one. I'm not gonna, what's it called? I'm not gonna go into this too much in detail. But there's one property about this this algorithm that is important for our proof. So this is why I'm doing it. Star square. Sorry, I think it's j less than I actually. Okay, I might have it wrong. If you have Wikipedia open, you can probably check. But the entire gist of it is actually that it orthogonalizes, starting from the beginning all up to the end. So what actually happens is that if I take this one, like the last one, it's going to be pairwise orthogonal to all the, sorry, the last orthogonalized one, so I'm saying like Vn star is actually, what's it called? It's orthogonal to every single previous one. That's how, so we basically have like an orthogonality clause depending on where we are in our loop, in a sense. So we actually use this for our proof. So what it matters is that this is interesting to look at, but the main gist and why I wrote out the sigma is just because you can kind of see that this loops for every single index before the one that we're going into. And the reason why it stops at the one that we're going into is because we don't have this quantity yet, right? We don't have the orthogonalized basis vector yet. So it loops through this and it gives us one. But every single orthogonalized vector is pairwise orthogonal with it. But there's also another property in that every single, v star j for any regular v, so basically any of the original ones that has a smaller index, it's also pairwise orthogonal to that as well. So if let's take the x as some your index of, for example, your in your basis, the what's it called? We're gonna take the first non-zero index of our integer vector.
Those orthogonalized vectors are still linearly independent, right?
Yes, of course.
So earlier you said you can't make a lattice from them at all. I thought you could make a lattice from any linearly independent
Vectors, right? But you can't. But they don't necessarily give you the same lattice, though.
It could be different.
Yes.
You still have a lattice.
You could, but part of the, if I remember, part of the problem is yes. Yeah. I might be wrong about whether you can't make a lattice with them at all. I forget exactly why I said that, but I read it somewhere. But I might be wrong about that. So typo on my end. I might if that ends up being the case, I'll correct it in the slides later on. So anyway. Remember that what we're basically trying to minimize is that when we pick some vector in B in, remember that we're trying to find the shortest vector, right? And then we also have our lattice in terms of a linear transformation. This is why I brought up an integer vector. Remember that our lattice is either the linear combinations, or you put it in a matrix, you take an integer vector, and you multiply them, and you also get a vector, right? So we pick some integer vector, right? It's pretty arbitrary. Then we take the smallest, or actually no, the largest index that is not a zero, basically. So if there's a zero at the end of it, then we take that one. Sorry, we don't take that one. We take the one before. Just so basically the last index that isn't a zero. And we basically take. We're going to use the properties of the dot product that we covered earlier. So we take our vector. Remember that bx gives us a vector. And then if we take the dot product of bj, which is our orthogonalized j, it's basically the vector index, the orthogonalized one. Well, the sigma on the right there is just the definition of the multiplication. That is essentially the same thing. Bi is not an element. Remember that Bi is a vector. So it's like if we saw the matrix column wise, it's very similar to it's exactly the linear combination. It's exactly that. But there's a good reason why it's written like that. If you guys remember pairwise orthogonality now, this is where it's cool. Now if you actually take the dot product of this, right? Because Bj is essentially kind of like a constant quantity. You can move it inside of the sum, right? That's just a property of arithmetic sums. You can always it's the same thing. When you have a where is this? Oh, I'm blind. Oh my God, I don't want to knock over my laptop. No, I mean just in case anyone's confused. Remember that any arithmetic sum is just a plus b plus c. I'm going through this because I'm seeing a lot of confused faces of how the hell I moved it in there. This is some arithmetic sum, right? Or sorry, let's put it in terms of a. So like a1 plus a2 plus A3, right? This is our arithmetic sum of, or sorry, just our sum, not necessarily our arithmetic, but the, let's say I less than some n of AI, right? Now, if we multiplied every single one by some constant, we would have like, CA1 plus CA2, blah, blah, blah. We can always factor out the C, right? Which is the same thing as moving it inside of the sum. Okay? Seeing the confused faces disappear, which is great. Now, consider our C, our orthogonalized vector. And the reason we can do that is because it's not really dependent on the actual sum itself. Now you guys remember that that's basically it. We moved. This is just a property of dot products in general. They are distributive over addition. So if you have a plus b, and then you take the dot product of a plus b and some vector, the same thing as doing dot product of a plus the dot product of like a and the vector and dot product of b and the vector. So it's just distributive, the regular distributive property, meaning that we move the dot product inside of the sum. But guess what? We annihilated everything. Everything except, sorry?
Are those equalities?
Sorry, what?
Between
Yes, they are equalities.
last two steps?
Yes, you'll see why very soon. Well, that's fine. You can. It's totally valid to move the absolute value in that way. I'll get there. Don't worry. Anyway, so basically, we notice here that this is distributive over addition, but because every single I less than j is like pairwise orthogonal, they all annihilate. So the only thing that you're left with is bj and bj orthogonalized, and those are not pairwise orthogonal. So that's the only thing that you're left with. So you have the dot product of that. And this uses also another property of Gram-Schmidt or like orthogonalization in that bj and bj like orthogonalized is the same thing as bj and bj orthogonalized. It has the same dot product. It's just a property. So you simply just rearrange, and if you remember, that's just the dot product is related to the Euclidean norm that way. So when you take the dot product of the same vector, is the same thing as taking the Euclidean norm squared. And so now we have basically kind of like an equality for our dot product. Ooh. So now, because we know of Cauchy-Schwarz, which gives us basically a upper bound on any dot product, it's just playing with variables at that point. So you state it in terms of Cauchy-Schwarz. Our original one. Wait, yes. I totally skipped a step, but basically this was just this was supposed to be a that should be bj squiggle. So that should be xj normalized, orthogonalized j. But the whole point is that I just canceled the orthogonalized j on both sides, right? And then in this second step, I basically just mushed two steps together. Like imagine the right-hand side inequality, I just remove it. So you get the inequality on the left, and then of course this is xj times bj, and because this is an absolute value, it is of course an upper bound to b orthogonalized j itself, which is again lower bound by the minimum. And I'm really sorry that I forgot the squiggles. But the entire point that I'm getting at is that this proves that our smallest vector is actually lower bound, at least by the orthogonalized one. And so we actually have a concrete lower bound. That's pretty cool. So with this, we can actually prove discreteness. It's super easy now. If you just take x to be some sort of I'm not gonna actually do it. But if you just take x to be some sort of difference, you can find a minimum for the x. So if you take basically some difference of vectors, with this inequality that we have now, we can prove that there exists some smallest vector that's lower bound by some quantity. And that basically proves the actual discreteness property of the lattices. I feel like this proof was kind of confusing, but unfortunately I should have probably covered Gram-Schmidt beforehand, or else it would have been more understandable. But I guess just the takeaway is we found a lower bound. That's pretty cool. Now we just need to find an upper bound. And basically, this is a fairly long, well, not really long-ish, but it requires a different theorem. 30 minutes, okay. It requires a different theorem to prove. So I'm just going to state it. That's just the Minkowski convex body theorem. And it's just basically saying that if you have a convex body, so think about it like a ball. It doesn't have to be a ball. So it's not exactly a nice radius. But if you have kind of like this blob, right? You can and you have this blob, and the volume of that little blob is greater than 2n times the volume of the parallelepiped. dl is the same as the volume of the parallelepiped. Then that amorphous thing contains at least one point of your lattice. That's what matters. So all Minkowski says is that we can find, with this little ball theorem, we find a point. We can prove that there's at least one point in there. So I forgot to add a space there. Dimension ball. So anyway, now that you have a lower bound and an upper bound, now that you have a lower bound, we actually want like a concrete upper bound. And this is Minkowski's first theorem, which you can prove with the convex body theorem. But I'm not going to get into that proof specifically. I want to just establish that this square root n times the volume of the fundamental parallelepiped to the power of 1 over n is actually our upper bound on our shortest vector. Rather, there exists some vector that satisfies this. So we have at least one. So we actually have kind of a bound above and below now, which is interesting. And now I'm going to leave the Hadamard ratio here. We're not going to prove that either, because I'm going to try to get into the cryptographic constructions. We don't have that much time. I went fairly slow on the proofs, but if you guys understood them, I'm super happy, because that's what I want you guys to really understand. This is now, we're moving on to actual applications now. Anyway, the Hadamard ratio just basically gives you a notion of orthogonality. So this uses something that's actually called the Hadamard inequality, which I didn't put. But the Hadamard inequality is actually really simple. It just basically says that the volume of the F is upper bound by, what's it called? All the vectors. So V1, the product of all of them. So actually, let's just use big pi. Big Emily pi. So anyway. Oh my god, my writing is so ugly. Okay, my bad. Hold on, I'll actually try. I'm sorry. I get in my own world sometimes, and I don't notice how ugly my writing is. Anyway, so the volume has an upper bound of the product of I less than n, where n is your dimension, of simply the product of all the Euclidean norms. That's what I meant to do in disgusting form. But that is your Hadamard inequality. So the Hadamard ratio is related to the Hadamard inequality. But what I want to illustrate with it is that it's actually kind of interesting, because the two-dimensional one actually gives you a fairly good notion of this, until you have to put it into like 50 dimensions. But if you think about making like any sort of four-sided thing, your largest area is going to be a square, right? It's going to be when these vectors are actually orthogonal. So when you have your Hadamard ratio is the biggest when you have all orthogonal vectors. So all your Hadamard ratio tells you is like how orthogonal is my basis. It gives you just a value between 0 and 1, where 0 is not inclusive. We'll use this value, but we're using it as a guideline. Why? Because it's cool. And we're actually going to talk about the first crypto system construction now of using lattices. This is the Goldreich, Goldwasser, and the guy that starts with an H. I forgot his name. Damn. Not Hadamard though. Anyway, it's the GDH crypto system, which is going to use this Hadamard inequality that we had. So, you know, we can actually notice something in terms of orthogonality, and this is actually why I said don't think about orthogonality until later on. What's it called? So, the Euclidean norm of, you know, of some vector degrades to this when the vectors themselves are pairwise orthogonal. It's fairly simple to show why. So if you guys remember, the Euclidean norm or the distance is actually related to the dot product. So we have this, right? We have this, okay? So when we want the Euclidean norm, we're gonna take the square root of the dot product, right? So, what's it called? We need two vectors. But now, if they are, what's it called? Pairwise orthogonal, then it turns out that this is a, wait, this would be, I think this means to say volume. Anyway, the entire point is that when these are pairwise orthogonal, this is actually really simple. Because this, for example, when you're relating two different vectors, they are 0, right? So why what's it called? When you're doing V with itself, remember that you can always write V in this form, right? You can always write V, any vector, in terms of the linear combinations of, you know, A1 V1 plus A2 V2, right? Then times another multiplication that is exactly the same. 1 V1, A2 V2, right? You guys know how to do multiplication and like distributed over addition, but every single one of these, when what's it called? When you have pairwise orthogonal basis, when you do, you know, A1 V1 times A2 V2, or sorry, plus, you know, sorry, it's like this. Yeah, anyway, when you take the dot product of each one, remember that dot product is distributive over addition, it annihilates, correct? So it turns out that the only ones that actually matter are the ones that are the same. That's the only ones that are non-zero. So that's why the Euclidean norm degrades to that really easy sum. So that becomes really easy to actually start finding the shortest vector, because you can compute Euclidean norm like nothing. And like maybe the shortest vector, like it might not be immediately interesting if you think about only the shortest vector. But for example, for the closest vector, we can actually use this fact, this orthogonality, to actually estimate, like with a very good, with a very good idea how we can minimize the coefficient to get our closest vector. So if we're looking for our closest vector problem, it's this, right? But now that we have to rewrite the Euclidean norm, because we know it's an orthogonal quantity, all we have to do is minimize the coefficients, right? And how do we minimize that? Now, the AI, it comes from W, and that's a rational quantity. So how do you minimize like that little difference? Fairly easy. Just pick the integer closest to that rational point. And we actually hit, and this is this is a fairly good estimate of the closest vector problem. You essentially solved it when it's when you have an orthogonal basis. So turns out that it's pretty easy when you have orthogonalization, right? But when you try this on an arbitrary basis, you actually get an estimate. You can try it, but if your basis is not orthogonal at all, then your estimate is going to be really far off. But if it's fairly orthogonal, then you're going to get pretty close to actually solving it. And this is actually what GGH is based off of, and actually NTRUE as well. And if we don't get to see entry, that's fine. It's not a big deal. So first to understand GGH, we just have to see Babai's algorithm, but that's kind of like the common sense that we just talked about. It's like how do we minimize the quantity of a vector times closest to another vector? Just write it in terms of a linear combination, right? And then take the closest integer point.
What is
I think that's rounding. Yeah.
round up?
Or just round to the closest. I guess because if you're exactly in the middle, just pick whichever one.
You round to the closest coefficient.
Yes. Yeah. I mean, if you think about it, that is the easiest way that you like if you view it graphically. Like if I give you a point here, right? Like which is the closest lattice point? Well, we have if we have the linear combination of this W, then we pick clearly this one is the closest point.
Right,
So
it's an arbitrary vector.
yes.
What is that notation?
Oh, which one?
Set AI equal to TI? Like,
Oh no, that's what Emily was asking. I think that's just rounded the closest. That's just the closest integer to that rational point. That's it.
And that would be just like comparing distances.
Yeah. No, they're scalars. So it's just the closest scalar point. They're not vectors. T1 is a scalar. There's a scalar quantity.
What that is by some-
No, yeah, of course, but but you don't need to do like anything fancy. And with this, you can actually use the first, we can actually make our first cryptographic construction, and it's Goldreich, Goldwasser, and Halevi. That's what it is. So let's say Alice. Every cryptographic explanation starts with Alice and Bob, but oh wow, I just noticed there's a comma under my name. That's weird. Anyway, yeah, who yeah, that's like the opposite of what people do. Sorry, I just noticed that, and it's been almost 2 hours. Okay, so we can choose what we call a good basis. Let's choose a good one, and by good it means we want it to be reasonably orthogonal. Not exactly orthogonal, but remember when I gave you that whole spiel about Hadamard? Well, that's why. You use the Hadamard ratio to figure out, this is pretty good, right? So that is actually your private key. That is what you're going to use to encrypt and decrypt. Let's denote that specific matrix formed by that good basis as a V, right? Then you pick a unimodular matrix, but you're glad I went in depth into those, such that we have some W, some other basis, as a result of the unimodular basis times the vector. Doesn't matter if it's left or right multiplication, just whatever. It can be actually a randomly chosen elementary matrix. As long as it's unimodular, it's fine.
So your public key
So you're actually the column vector is the column vectors of your W, of your randomly chosen one, is your public key now. Right? So Bob wants to send us a message, and he chooses a plain text M in the form of a vector. Right? So he just chooses a vector. He encodes his message as a vector, like encoding hello in terms of a number of vectors. That's actually how data goes over the wire. So similar idea. And then he chooses his message that he wants to send, and he chooses a random, what we call a perturbation vector. It's just a small vector, which we call R. So if you're familiar with nonces in cryptography, it's like our lattice nonce, in a sense. Kind of. Anyway, yeah, it's a vector style nonce. So to encrypt, Bob simply computes this quantity, which is Wm plus R. So just for the record, if you end up, if you actually like this talk, and then I'm going to open a textbook. Depending on which textbook you open, you might see this as Mw plus R, and on the Wikipedia as Mw plus R. The reason it might be different is not because my notation is wrong, is because I introduced W to you as a column-wise vector. If you would reverse it if the other ones usually put your basis vectors in rows. That's why. That's the only reason. Amateurs. Okay. Anyway, that is his ciphertext. So what we do is, now that we covered bye-bye, okay, I'll make that joke later. It sounds like a are you getting that? Do you know what I'm talking about? Bye-bye. Okay, anyway, now that we know about Bye-bye's algorithm, and we have our good basis, and we also have a unimodular matrix, remember? So we can actually transform it. So Bob basically made his linear transformation in terms of the shitty one. We can recover it by taking the inverse, right, of our shittily chosen matrix, right, and then you know, with the inverse we turn it back into our good basis. And remember that our good basis is reasonably orthogonal. So our good basis, when we try using Bye-bye's algorithm to find what M is, like what our closest vector is, we actually get a really good estimate. This is why orthogonality was really important, in that the jumbling, the cryptographic confusion, is in terms of, you know, switching bases. But we kind of stopped there with this because it actually turned out that a guy called Nguyen, he kind of broke the whole thing in 1999. So, but this is kind of like the cool motivating example. It's like this is like the first thing. I think this was the first one that was released, like the first lattice cryptographic algorithm. And that's pretty cool. It's so that, you know, just using the CVP, we can actually hide some amount of information. So then, yeah, I think we're gonna have enough time to review. Yeah, we have enough time to cover NTRU. NTRU is a little bit more complicated. So it's not NTRU, it's NTRU. I don't know, edgy name. But it basically requires just a tiny bit more of an abstract algebra to understand. Now, this is the ring of convolution polynomials. That's just the name I found it in literature. I couldn't even find the Wikipedia page on it, but I mean, it is what it uses. But I think there's actually another formal mathematical name, because this is in general just a polynomial ring, right? Where, you know, Z is a field, and it is a ring because are you guys? I know that I assumed that you guys knew some group theory, but I didn't assume that you knew some ring theory. So, are you guys familiar with quotient rings? No, well, okay, you are. You don't count. But okay. So anyway, the entire point of a quotient ring is, again, I don't really mind if I go on this tangent, because remember, this isn't foundational. So if you get the algebra part, that's even better. Because I don't want you to memorize NTRU. I just want you to get the underlying math, because you can, after you get it, you can just reread this and you'll get it in 2 seconds. But anyway, you guys have seen. Okay, this is something you've definitely seen. You've seen, for example, the ring modulo, like the field of integers modulo some q, is denoted like this, right? But then this is isomorphic to some notation that some people use that looks like this, right? People think they're the same. They're isomorphic. They're not exactly the same. Sorry? Sorry? Yeah. No. This is just the integers modulo q. Just you know, a in z, a mod q, and let's assume that q is prime. So this is isomorphic to what is called what's it called? The quotient ring or field, depending on whether it's a field or not, depends on whether this M is actually prime. Or sorry, this is ZQZ. Sorry, but whether if Q is prime, this is a field. Oh, that's what you meant? Oh, my bad. Yeah. Anyway, I meant these are exactly the same, but the reason that this works is that there's a notion called a coset, which we show that, what's it called? How a coset relates to kind of like a modulus, and how a quotient in a sense is a sort of modulus. So let's start with only QZ. What is QZ? Is you take every integer right? You take, what is an ugly squiggle? You take, QA for all A in Z, right? So this is a group that's called cyclic, because eventually, because it's generated by one single kind of element, which is like just QA. Wait, no, is it cyclic?
Yeah.
Yeah. Okay. Anyway, well, it's generated by Q rather, but you can essentially every element is of this form, and the equivalence classes. So all the elements that are the same is, for example, if you have like let me see an example. Just any number that's divisible by Q, to some extent. Like that's how you make like conjugacy classes of this. So I guess the easiest way is if I show you 2z, right? I wanna what's it called? Expand it until so that I can explain cosets, and then I can explain what a quotient is. So with the quotient, then you can understand the quotient ring. So 2z is just gonna be like just dots, -4, -2, 0, 2, blah, right? Okay, so this is just this it's just this is what we call just a we can think about this with addition. If you combine this with addition, this is just a cyclic group generated by the number 2. But what happens when you take something that's called a coset? We're going to talk about specifically the left coset. So if you take the left coset of this, so take any number in so let's pick some random a in the integers. And now, what is a plus 2z? Well, depends on the a, right? So in the case of 2z, it's super easy. Your number is either odd or even. So if a is 1, right? Well, you actually have 3 cases. You always have the identity, of course. So if a is 0, then you have. So if a is equal to 0, then you get just the ring 2z, right? If a is equal to 1, then your ring looks more like this. Looks like or your set, I guess, looks like -1, 1, 3, blah 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 blah, right? But when this a is 2, then you go back to the same thing. Like if this a is 2, you have 2z again, because you do 0 plus 2, you get 2. You get -2 plus 2, you get 0, right? You get the exact same infinite set. So it turns out that these two elements, a0 and a1, define an equivalence class. And this notion of a plus z, this is the coset, the left coset generated by a, right? When you take all the left cosets, or all the cosets in general, you get this, which is the quotient ring. So it's kind of like you can think about an element of z modulo an actual ring. Because you can think about it, like our little addition here is modulo the whole set. Because when we get a transformation on the infinite set that is exactly the same set, that's the same thing as a modulus, right? So if you look at how this has only 0 and 1, this is exactly the same as saying a mod 2, right? You only have 0 and 1 in the case of mod 2. So it turns out that these are isomorphic when Q is prime. So now that I've explained quotient, this specifically is a quotient group. A quotient ring uses a similar construction, except the thing at the bottom is something that is called an ideal. And ideals are kind of like the great annihilators. So if you have some ideal I, right? And this is sometimes called the dual-sided ideal. That is a subset of some ring. And a ring is just it's like an algebraic structure that is an additive group and a monoid. And then if it has a multiplicative identity, you call that a ring with unity. If the multiplication is commutative, that is an abelian ring. And if every single element has a unit, then you have an actual field. That's just algebra trivia. We don't really need to get too into it. An ideal just simply has the property that when you have any A in the ring, right, and then R in the ideal, AR, is in I, and RA is in I. So you can kind of see that this kind of annihilates it in a sense. Every single multiplication with an element of the ideal puts you back into the ideal. Yeah, it is a subset of the ring, but the reason I'm not talking about subsets too much is because the ideal, if the ideal is maximal, it could be that depending on, for example, when it's a field, the ideal is actually the whole ring.
Well, I'm trying to make a point of difference here because annihilators are.
No, I know you're talking about annihilator. For example, 0 is an annihilator in terms of multiplication, but I'm.
You have annihilating elements.
Right, but I'm not talking about annihilation in terms of turning it to 0. I'm talking about annihilation in terms of no. I guess it's not really annihilation. I'm just saying it's kind of like it's a black hole that sucks every element into the ideal. Yeah.
Under multiplication.
Yeah, but under multiplication of like every element inside of the superset. Yes. Anyway, why that's cool is that our ring there is that every polynomial that you can factor out by xn minus 1, it turns out that every polynomial that has a degree larger than xn minus 1, you can always factor it out into some polynomial plus xn minus 1 something. So because you can't have polynomials larger than that, that in itself is an ideal. That little xn minus 1 is an ideal. And because you have essentially like a ring, it's a field. Like you have the polynomial ring of integers, the polynomial field, over an ideal, then that's when you have a quotient ring. That is the definition of a quotient ring. And the entire point is this quotient ring gives us just a few cool identities. How much time I got? I got 3 minutes. Let's blaze through this. But the quotient ring was the more important part. The whole point is because of the fact that it's an ideal, every single polynomial that you make within that quotient ring is kind of divided in a sense by xn minus 1. So your degree of your polynomial inside of that quotient ring is at most xn minus 1 in this sense. Xn minus 1 here. But the degree of, like the highest degree of a polynomial you can have in this R is x to the power of n minus 1. So it turns out that you basically take a modulus and you can define basically the multiplication of every single polynomial within that field in terms of that. Just very simple modular arithmetic. That k minus I is also modulo n, so if that goes negative, then it's the same. You just loop back around, and then you have the central lift of ax to r is just some unique polynomial, such that like when you take the modulus of it, you get ax back. So and remember, ax is in rq, so rq is the ring, and the coefficients are modulo something. A prime is there's no modulus. And hey, if your q and rq is prime, then if the polynomial is relatively prime, actually it's the same exact definition as relatively prime numbers. And the whole gist of it, I'm going to skip it, is NTRUEncrypt uses this sort of shape to calculate your private key and your public key, which is in terms of central lifts. From some ring into another ring, and then due to the certain choice of constants, you can always reverse it. But again, this doesn't matter. It's cool to see, but if you guys got the lattices part, I'm super happy. That was the goal. This is just applied. This is applied everything you've seen so far, plus like a smidge of ring theory. And the rest of the slides just go over NTRU. And just the very basic gist of it is that you keep the constants between some range, you pick some functions of some what you call ternary polynomials, and you encode your message as another polynomial, and you just apply a bunch of different congruences and multiplications until you can, you jumble your message one way, and then you can unjumble it. And NTRU has a lattice equivalent in that lattice, which is looks kind of nuts, but it's actually very simple. It's just the identity, right? Then H is your public key, and then identity on the left, then that's the 0 vector, and then on the bottom right, that's your Q, your modulo Q times the identity. And when you apply that multiplication, what's it called? You apply matrix multiplication on that, and then you actually get the quantity that you want. And that's NTRU in general, NTRU in a nutshell. This is not the most important bits, but it's a cool application. And if you decide to go through the slides, you can check out the algorithm and how it works, and also like you can make your own little congruence proof. And that concludes our talk for today. Thank you. If you want to look more into it, I actually provided every single resource I used to make this talk. So the first one, the top one, is Dr. Chris Peikert's lecture notes from his graduate course. The second is the lecture notes by the father of the most modern construction right now, which is Learning with Errors, Oded Regev. Then the book by the people that made GGH, or by one of them, is a great one. It's called The Complexity of Lattice Problems. That is one of the most rigorous ones that there are. And then there's also a few notes by a professor from MIT. And then for the algebra bit, I suggest Arden is pretty good. I like Arden. Screw you. The foot is too dense. I'm not that thick. Anyway, and then for cryptography, for basic cryptography, it's one of the great series of undergraduate texts in mathematics, Introduction to Mathematical Cryptography. This has it's a little bit less rigorous than the other ones. So for example, the proofs of successive minima are not in that one. But for example, a lot of the diagrams from NTRU and all this stuff I got from there. So it's a great overview.